Swayam Prabha. Digital India. Educated India.
So welcome to the lecture on boiling heat transfer. So in this particular lecture, we will introduce what is boiling, and then we will see the nuances and the characteristics of heterogeneous nucleation. We will also introduce what is basic pool boiling and enhanced pool boiling. So these are the 4 points which we will be taking up in this particular lecture. As you will appreciate, before I proceed, you must understand that boiling or evaporation is a very important process. It is the phase change process from liquid to vapor. And of course, there are two words, boiling and evaporation, which we will see the differences very shortly. You should appreciate that this is a very important heat transfer process. Now, right from the Industrial Revolution, when steam engines came into existence, and then several machines which were developed by the steam power. So boilers, power plants, boiling water reactors, electronics cooling system will evolve. In the later part of our lecture series, we will take up some of the passive cooling systems or heat transfer systems. There, evaporation is a very important phenomena. Refrigeration, air conditioning is full of both the evaporator and the condenser have these processes. The evaporator has the boiling process, and the reverse takes place, the condensation process takes place in the condenser. Several chemical reactors involve phase change processes. Cavitation is also a phase change phenomena. Flashing flows, mechanical boiling. In petrochemical industry, distillation takes place by successive boiling of the mixture of petrochemicals or hydrocarbons. Distillation columns, simple coffee machines which you see, the high pressure coffee machines, they make use of bubble pumps, which also utilize boiling heat transfer. So this is a series of applications and very important for many industrial and technological processes which involve this type of phase change boiling process. So now let us try to understand the difference between evaporation and boiling. So if you see, evaporation is the process of conversion of the liquid phase to vapor phase at an interface, and we are all aware of atmospheric evaporation which takes place from rivers or oceans surfaces. Now what is important to understand is that evaporation is driven by a concentration difference between the liquid phase and its vapor. If you will recall in your thermodynamics, the specific Gibbs free energy of the liquid phase and the vapor phases are different here, and therefore this concentration difference drives the molecules of liquid to get converted into vapor. The overall system pressure may or may not correspond to the saturation temperature. For example, our wet clothes are dried in the atmosphere. At that time, the normal boiling point of water is 100 degrees centigrade, but the evaporation does takes place at a lower temperature. Even when the atmospheric temperature is 20, 25, 30 degrees and the relative humidity is not 100%, then you will see that the wet clothes get dried up. So the driving force is the specific Gibbs free energy difference between the liquid phase and the vapor phase, and therefore to achieve equilibrium the liquid will continue to evaporate, and that is definitely not boiling. Now when we say boiling, then we are conversant with making of tea, for example, every day, and there the liquid, actually the temperature gets heated up to 100 degrees, and in this case the liquid vapor system temperature corresponds to the existing saturation vapor pressure, and the liquid is typically heated slightly above the saturation temperature. That is what we will see in this lecture. At that time boiling takes place. So this is a heterogeneous boiling in a sense that there is a solid surface on which the liquid is bubbles are getting formed. So please try to understand the difference between these two processes. The evaporation, the temperature, may or may not corresponding to the local saturation temperature which it should be, but still phase change takes place. So with this major differences appreciated, we will concentrate on boiling heat transfer in this particular lecture. So when a liquid is in contact with a surface maintained at a temperature above the saturation temperature of the liquid, boiling will eventually occur at that liquid solid interface. Now there are various mechanisms of boiling. They are named as, these are new keywords to you: nucleate boiling, convective boiling, and film boiling. Now, in nucleate boiling, whenever we say nucleation, that means vapor bubbles are being formed. So whenever bubbles are formed, typically on a solid surface, we call it as nucleate boiling. Then convective boiling is when no bubbles are formed, but a thin film evaporation is taking place. So you will see several examples in, for example, in refrigeration systems, when in the evaporator, at the at the end part of the evaporator, when the liquid has become less now, bubbles have stopped actually, but a thin film evaporation starts. So essentially inside a tube, for example, there will be liquid on annular type of a flow, when there is a liquid here, and there is a strong vapor flux which is getting formed because heat is coming from outside. Such a type of situation is called as convective boiling. Then there is film boiling, where a blanket of vapor on the heated surface. So essentially in this case there is a vapor, the vapor is here and the liquid is on the top. Okay, so this is liquid and this is the vapor. Okay, and in under such conditions, heat is coming in from this surface here. We call it as film boiling. So these are the three mechanisms of heat transfer, and the morphology of the liquid and the vapor is different in nucleate boiling, in convective boiling, and in film boiling. Now typically there are two geometries. One is pool boiling. It is like while we make tea, you have a pool, and in this pool there is no external. So if you just take a pool here, you take a vessel, put some liquid in it and start heating. Now this is a stagnant liquid. And as the temperature increases, bubbles will start forming, and there is no external active flow which is taking place in this particular pool, and therefore this is called as a pool boiling. Now in flow boiling, there is usually a channel, in which a pump is pumping some liquid, and as the heat comes in, bubbles are getting formed and they are getting convected inside this tube. So this is called as a flow boiling phenomena. So we will be focusing mostly on pool boiling in this particular lecture series as we go ahead. So if you see from a fundamental point of view, the heat transfer during boiling. So we are interested to find out what is the heat transfer coefficient at the heated surface when such boiling is taking place. As I said, we'll focus on nucleate boiling. So what are the characteristics? So the first of all, the wall temperature is slightly higher than the bulk temperature. So bulk temperature corresponds to the saturation temperature in most normal cases. It can also be subcooled, but right now we will consider that the bulk temperature is equal to the saturation temperature of, let's say, if it is water and 1 atmosphere, then it is 100 degrees centigrade is the bulk temperature at P equal to 1 atmosphere. So this is a typical tea making at home. So the water first starts with room temperature, but then fully developed nucleate boiling will start at 100 degrees centigrade bulk temperature. So there is a delta T. Then the bubbles are formed. Bubbles are lighter than the bulk liquid. So naturally the density of the vapor is lower. So the bubbles will tend to rise upwards. So there is a buoyancy force G delta rho, which is affecting the process. Then there is a latent heat because phase change is happening. So if you recall our pressure enthalpy diagram, then this is the pressure, this is the enthalpy, and the saturated liquid is getting converted to saturated vapor. So this is the vapor point, this is the liquid point here, this is the liquid line, and this is the vapor line here. So therefore the latent heat is the change in enthalpy of the liquid from going from saturated point to saturated vapor. And then there is surface tension because of the formation of the bubbles. You have interfacial phenomena taking place, surface tension. There is a typical length scale. The length scale can be the size of the bubble, for example. The densities of liquid and vapor is playing a role. The specific heat of the liquid is playing a role. The thermal conductivity of the liquid is playing a role. And the viscosity of the liquid, because the bubble has to now travel upwards. It has to first grow. It has to push the liquid away and then grow and then leave the surface and then travel upwards. So there is friction which is in the form of the viscosity of the liquid and the vapor. So if you apply the Buckingham Pi theorem, you will see that certain non-dimensional numbers come up, which are pretty straightforward. So let's first discuss these four non-dimensional numbers. So this Cp delta T by HFG, this is the sensible heat divided by the latent heat. This is called as the Jacob number. Mu Cp by K is well known. This is the ratio of the thermal, the momentum flux and the energy flux, this is the Prandtl number, which is well known to you. And then here is the scaling of the buoyancy force to the surface tension force. The buoyancy force wants to take the bubble upwards, and the surface tension force is trying to hold the bubble. So the ratio between the two is called as the bond number. When the bond number is high, which means the buoyancy is dominant, and when it is low, it is the surface tension dominant systems. And then you also see another interesting, let's say, non-dimensional number, which is the buoyant force divided by the viscous forces, which strongly resembles the Grashof number which you have studied in natural convection, in the lecture on natural convection. It is a very similar phenomena happening here. There hot air was getting moved upwards because of buoyancy, and the viscosity of the air itself was the force which was trying to stop it or break, create the resistance. In case of boiling, the bubble wants to go up because of buoyancy, and the viscous forces of the liquid are the ones which are posing the resistance to this motion of the bubble. So you see the Nusselt number now depends on the Jacob number, the Prandtl number, the bond number, and this Grashof number looking type of a number, which is also called as the buoyancy number, or the effect of buoyancy induced flow motion, is what is captured by this number. So there are four basic, let's say, non-dimensional numbers on which nucleate pool boiling will depend. So let us see how to, so one can have experiments which connect a Nusselt number to these four parameters, and there are other methodologies also by which one can create, let's say, expressions for Nusselt number which are based on the scaling analysis which we have just done here. So before we proceed to the actual pool boiling, when hundreds of bubbles are, are getting formed and released in the pool, first we will see a simple nucleation of a single bubble. So nucleation can occur in two ways. One is the homogeneous nucleation, and the other one is what is called as the heterogeneous nucleation. Now, homogeneous nucleation, when a bubble gets formed, in a liquid volume, completely within a superheated liquid. So if the liquid is superheated, of course, it needs to be superheated so that heat can be given to the bubble. The bubble doesn't require any solid surface to get formed. It is inside the bulk itself, inside the volume itself. So it's a volumetric phenomena. But when we make tea, for example, the bubbles do not get formed inside the volume. They actually get formed in on the surface. So as you can see here in this figure, so they are forming on the solid surface. So when bubble nucleation takes place at the interface of a solid which is in contact with a superheated liquid, it is called as heterogeneous nucleation. So in our discussion in this lecture, all our discussion will focus on heterogeneous nucleation. It will be we will not consider homogeneous nucleation, which is slightly different phenomena, but we will consider only heterogeneous nucleation. So you can see here heterogeneous nucleation taking place. Videos are shown, and you can see one bubble which is getting formed and rising up. Some new bubbles on the right can also forming, and they are merging also. Some of the bubbles are rising, but they are becoming smaller in size as they go up, because it is possible that the liquid on the top is subcooled. The entire liquid is not saturated, and therefore in this particular case you can see the bubble actually becoming smaller as it rises, because on the top it is cold liquid, or colder than the saturation temperature or lower than the saturation temperature, and therefore condensation takes place and the bubble becomes smaller. You can also see bubble merging. Two nucleation sites which are close to each other, you can see they are interacting with each other as the bubble rises, and these are slow motion videos. So you can appreciate how a bubble gets formed on a nucleating cavity, and then slowly becomes bigger and then rises. So these particular sites, where these bubbles are getting formed, they are called as nucleation sites, or they are called as specific nucleation sites. So nucleate boiling depends on number of active nucleation sites on the surface. So the idea is how many bubbles, how many nucleation sites are active, which means active means they are in a position to create a bubble and sustain its growth. So therefore, the type of surface, whether it is smooth or rough or what type of cavities it has, that will depend on the boiling will depend on such type of surface morphology. So therefore, surface morphology plays a very important role in boiling heat transfer. So as we will study, these particular nucleation sites have a how will a site become active? So it has certain parameters to be fulfilled, so that the site becomes active. You must have seen while making tea also, that some of the sites, the bubbles will continue to come on the same site or same location again and again. And as the heat becomes more and more, more and more nucleation sites become active. So let us look at these surfaces from a microscopic view. So if you see any typical copper surface or something, it has a lot of asperites. It is rough, okay, and the cavities may be open cavities like this. They may be, some of the cavities may have a shape like this. Most of the natural cavities are like open cavities like this, and depending on the wettability of the fluid, the contact angle of the fluid, the liquid may wet the cavity or the liquid may not wet the cavity. So what happens is, when you fill up a vessel, with some liquid in it, as the liquid comes in, it starts interacting with the surface, and some of the cavities may, these rough surfaces, some of the cavities may trap some gas. Okay, so there are four types of cavities. Cavities that trap gas, cavities that trap liquid. Okay, for example, if the mouth is too big, then all the liquid will fill inside, and there will be no gas trapping inside the cavity. So we will not go into too many details about this process, but it is sufficient for you to understand that there are certain cavities which can trap gas, so that, for example, here in this cavity, the gas is or vapor is getting trapped, and some of the cavities can trap liquid as well as gas, and some of the cavities can neither trap liquid nor vapor. So this roughness, this natural roughness, may have different types of shapes. We cannot analyze all the shapes, but we can model them as conical cavities with a certain angle and a certain depth. So before we proceed to understand how a bubble actually grows or forms and then subsequently grows on the surface, let us first try to understand the Young-Laplace equation, which you have also studied in your earlier years. So whenever a surface is formed, that's an interface between a liquid and a vapor, for example, it will that surface, just because of the existence of that surface and of a stable surface, it comes in equilibrium because there is a pressure difference which it sustains across it. So this is very simple mechanical way of understanding. So let us assume that we have a surface, and as the bubble grows, we are actually creating new surface. So this surface is growing now. So we are trying to understand how this growth takes place and what is the pressure which is required to sustain this growth. So if you see the original area, we can assume at x into y. So x is one dimension here, the y is the another dimension here. So these are the two dimensions. And then as the bubble grows or the interface grows, the new area becomes x plus dx and y plus dx. So that is shown in the second figure here. So what is the change in area? Now the change in area will be, you open up this bracket and subtract this. So new area minus the original area, and then neglect the higher order terms. So you will get dA is equal to x dy plus y dx. So now the question is that this area increase because a certain amount of energy is required to form this interface or grow this area. Some work must have been done. Then only you can stretch this interface, because the intermolecular forces are there which which are present and in this interface area, and they are attractive in nature. And if you want to make a larger area out of them, you need to stretch them, and therefore certain amount of energy is required. And as you will recall, this is the surface energy, which is represented by the surface tension. So sigma into dA will be the energy required, Newton per meter square, for this particular growth of the interface to take place. Now this is done because there is an internal pressure which has pushed the interface. So the phase 1 is pushing it so that this interface is now growing. So the energy which is provided in this push is the pressure difference, because the force has moved through a distance dz, and this force is equal to delta P cap into x into y. So that is the pressure into area is the force. The force has moved to a distance dz, so that is F times dz. So force is moved to a distance, so a dot product, which will give you the work done. Now this work which is done on the interface, if you do it reversibly, this gets stored into the interface as surface energy. So if you equate these two, you will get the equation which is called as the Young-Laplace equation, which is delta P cap is equal to sigma times 1 upon R1 plus 1 upon R2, where R1 and R2 are the radii of curvature, which can be related to the geometry x and y. So what we see is that whenever a bubble is growing, if you see a bubble like this, then there is an interface, and there is a pressure inside in phase 1, and there is a pressure outside in phase 2, and there is a pressure difference. So if the bubble is in equilibrium, then you will see that this delta P cap will always exist between the inside and the outside of the bubble. Okay. So the Young-Laplace equation is something which is fundamental to the growth of an interface and growth of a bubble. Now, what is the next condition? There are two conditions. This is a mechanical condition of stability, and the other condition which comes from the thermodynamics. That will come from the Clausius-Clapeyron equation. So how will, if you recall your Clausius-Clapeyron equation, what it tells you is it relates the pressure, the pressure condition to the latent heat of the system. So I will not derive this, but you will recall from your thermodynamics that the dP/dt, or the rate of change of saturation pressure with temperature, is given by HFG divided by nu g minus nu L into Tsat. As the bubble grows out of the cavity, so we have assumed an ideal cavity here, which is conical with circular opening, and the entrapped gas, the disturbance will travel and the heat will come in from here, and the bubble radii will, the inside the cavity will change, and then it will come on the top. And now if it has to grow further, then this Clausius-Clapeyron equation must get satisfied, and simultaneously, as you will we just saw, that the Young-Laplace condition should also get satisfied. So as the bubble grows, the Young-Laplace equation and the Clausius-Clapeyron equations are simultaneously valid. In this, of course, we assume a quasi steady growth, and there are no metastable conditions. The bubble is growing, and so the minimum radius of curvature occurs when the bubble forms a hemisphere at the mouth of the cavity, and therefore the radius of curvature is then of course equal to the radius of the cavity of this particular cavity opening. At that time you have the minimum radius and the maximum delta P because of this. Since these two are related thermodynamically through the Clausius-Clapeyron equation, as the bubble is growing, both of them should be satisfied so that the bubble can come out. If any one of them is, if the conditions are such that any one of them is not getting satisfied, then the bubble cannot grow out of that particular cavity. So you see, you have the PB minus P is equal to 2 sigma by R is the Young-Laplace equation, and as the bubble grows, its radius changes, and you can get the excess pressure. So the PB is here, the saturation pressure is here, and if you want to put the heat inside this cavity, you must have the wall temperature which is larger than the saturation temperature by a value which is given by the application of the Young-Laplace equation and the Clausius-Clapeyron equation. So therefore, you will always see that if the saturation temperature is Tsat is 100, then depending on the radius of the cavity of a particular cavity, the wall temperature, the T wall, must be higher by a certain degree. So maybe 105 degrees or 106 degrees, depending on the value of 2 sigma by R. R is the radius of the cavity here, the size of this cavity here. So now in a real system, there will be smaller cavities, there will be larger cavities. So not all cavities will become active. Only those cavities which satisfy this condition at a given operating condition of T saturation, the surface tension of that particular liquid, the latent heat of that liquid, so those are the only ones which will become active. So this formula actually comes by the application of the Young-Laplace equation and the Clausius-Clapeyron equation, as you can see here. And if you substitute this in this, you will get the condition for a particular nucleation site which will become active. So we can use this formula and plot how much is the degree of superheat. So what is superheat? The temperature of the wall and the temperature of the fluid. So Tw minus Tsat is what is delta T here. This is Tw minus Tsat. Okay. And the cavity radius R, which we just got from in the previous slide. So what it tells you is that as the level of superheat becomes higher and higher, so if you keep on increasing the wall temperature, you will see that a smaller and smaller radii, cavity radius becomes active. So you can see here, okay, so R becomes smaller and smaller. So what it actually means is that when you increase the delta T, more nucleation sites become active. So if you just calculate, if you put the values for water at 100 degrees centigrade at 1 atmosphere, so water at 1 bar with a degree of superheat of 5, you will see that the radii comes out to be about 6.5 microns in that equation on slide number 13. So what it means is that all the cavity radius which are 6.5 microns, uh, are active, and as you increase the superheat to 6 degrees, 7 degrees, more smaller and smaller cavities will become active. So as the degree of superheat is increased, cavities of smaller and smaller radii become active and initiate nucleation. So in the beginning, a cavity with a larger radius is active, and a smaller which is a smaller radius is actually inactive. That means bubbles are not getting formed because they are not satisfying the Young Laplace equation and the Clausius-Clapeyron equation. But if you increase the delta T, now they will start at a certain time, at a certain temperature, they will start this cavity, smaller radii cavity will also become active. So this is how uh, you know so what it actually means otherwise also is that if you have a very smooth surface, then the degree of superheat which is required is very large. So if you have a rough surface in a heterogeneous nucleation situation, the let's say you will have more and more nucleations happening uh, on a typical rough surface. So if you really take a smooth glass surface with a very actually no roughness, then it is very difficult to have heterogeneous nucleation, or the degree of superheat which will be required will be very high. So if you take a smooth glass surface, you may have to put the temperature of at 115 120 degrees, then only some bubbles will be formed. But if you take a rough surface, then even at 103 104 degrees centigrade of the wall temperature, boiling will start. In reality, of course, you will see that in the denominator I have put something like a function of contact angle and the mouth radius. So in reality, of course, wetting also will play a small role. But if you neglect the wetting, the Clausius-Clapeyron equation and the Young Laplace equation together give you the condition for heterogeneous nucleation on a particular rough surface having a particular radii r. So this is how you can find out which cavities will be active and which cavities will not be active at a given wall superheat. So before we proceed, let us look at some of the videos of bubble behavior on smooth surfaces. And here you can see, how a bubble is growing on a surface. You can see the bubble slowly getting bigger, buoyancy taking place. Now the bubble starts rising up. There is a neck region here, and now the bubble grows. And now, because the bubble has moving upwards, it is creating a low pressure area behind, and the liquid gushes in, the cold liquid gushes in from the sides, and you can see it once again if you want. How does it grow? You can also see the contact angle of the bubble on the surface, and you can see some surface ripples, and now the necking starts, and now the bubble departs, and as it departs, because of the fluid mechanics behind the wake of the bubble, there is a reflux which you can see, and the bubble now goes away from the surface. Similarly, in the second video you can see another nucleation site, and then there are two sites now, in fact 3 or 4 smaller sites. Now the queue is slightly larger, and you can see more nucleation sites becoming active. There is also some merging taking place because of these interaction of the bubbles which are forming from close by nucleation sites. Now as you increase the roughness, You can see now in the third video, you can see some rough surfaces. Now many nucleation sites are active, and they are strongly interacting with each other. You can see merging, you can see simultaneous nucleation, you can see bubbles which are rising, and growing from various nucleation sites. And if you increase the roughness still further, you can see a lot of bubbles. In fact, now it is very difficult to make out individual bubbles. The nucleation sites are becoming are quite large in number because of the higher roughness of the surface, and you can see now fully developed nucleate pool boiling taking place on these surfaces. So very interesting videos. The videos also show you a lot of physics. They also see that the bubble merging takes place, buoyancy starts, there is agitation which takes place because of this bubbling motion, and since there is no external pressure to move the fluid, to move the pool, the pool is getting disturbed uh, by by the agitating bubbles themselves. So we also see that as the bubble grows, it interacts with the surface, and there is a certain contact angle. Depending on the wettability of the material, the certain contact angles are getting formed. So before we close, this particular lecture, we should also understand that contact angle plays a role. As I said earlier also, that even when we derived the formula for active nucleation site radius, we saw that in reality there is a function of contact angle which is also played by the contact angle also plays a role in the activation of the cavity. So let us try to understand this contact angle. As you know, when you put a droplet of liquid on a solid surface, depending on the wetting condition, it can be either a poor wetting condition, so pearl-like shapes of the droplet get formed. Then the contact angle which is measured, you make a tangent here, and then you go from inside the liquid out towards the tangent and measure that angle, which is called as the contact angle. So this contact angle can be greater than 90, then we call it poorly wetting or hydrophobic surface. When good wetting takes place, it is between usually 0 and 90 degrees, and complete wetting means the fluid completely wets, so the contact angle actually tends to 0, almost nothing, it just spreads like a thin film. So these depending on the liquid and the solid combination, you may have poor wetting or good wetting and completely wetting. These are some of the photographs. Now another phenomena which takes place in wetting is called as what is called as hysteresis, and here you can see on the right two photographs. If you take a horizontal a sessile droplet on a horizontal surface and then try to turn that surface in an angle, then you will see that the advancing angle and the receding angle, the advancing angle is this angle here, and the receding angle is this angle. The droplet is tending to move towards this direction. So the advancing angle, which is theta A, is usually different than theta R. So this is theta A, and this is theta R. Okay. So why is this different? This difference is called as in normal language we call it hysteresis or contact angle hysteresis. So for an idealized solid, perfectly smooth, clean and homogeneous, there is no reason that hysteresis should take place. But in reality, we see that hysteresis does take place because of surface inhomogeneity or roughness and the impurities which are there on the surface. What we call as spinning takes place, and because of which hysteresis is actually seen or manifested. So such type of hysteresis also plays a role in bubble growth or in pool boiling applications, and usually this is very complex. It is not so easy to let's say do an analytical expression for this function, but researchers have found out the effect of wettability on pool boiling and how nucleation sites get affected by wetting phenomena or non-wetting fluids and wetting fluids. So this particular hysteresis can also be measured by an experiment which is shown here. You have a plate which can be dipped and taken out, and while you take it in and out, the angle which is measured here, while taking in and while taking out, there is a difference in the angle, and this can also give you an indication of the hysteresis which is present on this surface in combination with the present liquid. Now, in reality, you can have a physically textured surface, or a chemically textured surface like this, which will also show hysteresis. And the theta, when you're moving in this direction, the advancing angle may be different than when you are moving the interface away from in the other direction. So it may be, one may be theta plus and one may be theta minus. Similarly, if you have a combination of two materials and the liquid is getting, one of them has a different contact angle, the another has different contact angle, depending on what type of surface energy distribution you have. Then when the interface passes through from one material to the other, the interface will tend to stick and change its angle from theta plus to theta minus, or theta minus to theta plus as you move the liquid interface on such type of topographically different surfaces, either physically varying topography or chemical varying topography. So this is basically the equilibrium sessile contact angle, and such type of on an inclined solid you will have the receding and the advancing angle different from each other, which will be theta A minus theta R. This will be the hysteresis, theta hysteresis, which will be usually observed in common engineering substrates. You have also seen such type of a behavior of the contact angle hysteresis. Because of the hysteresis, a liquid plug like a Taylor bubble plug or a Taylor plug, in a small pipe, you can actually apply the Young Laplace equation at position 1 and 2 and 3 and 4, and since the gravity is acting in this direction, this particular angle is different than this angle because of one of them is advancing, one of them is receding, and because of the hysteresis, if you apply the Young Laplace equation, it will be P1 minus P2 will be 2 sigma by r cap on the top, and here the r cap, the radius is different, and the top radius and the bottom radius is different, so 2 sigma by r bottom. And if you apply from 4 to 1 in the entire thing, there has to be the weight of the liquid, which is rho GL and rho LGL, and therefore if you substitute it in the Young Laplace equation, you will see that a certain mass of this particular plug gets supported. If you keep it, it will not move downwards. Because this contact angle hysteresis, that is 2 sigma 1 by r top minus 1 upon r bottom, this capillary pressure difference which gets created because of the fact that hysteresis is taking place, then this particular capillary pressure difference supports a certain length of the plug or the weight of the plug. Of course, if the plug is becoming larger and larger, then it will start falling down. but a certain amount of liquid plug can be trapped without motion in equilibrium in such a tube, such a small tube in which surface tension dominates. And so this is a direct example or a manifestation of contact angle hysteresis. So this hysteresis plays a role in wetting the cavities, in entrapping the gas inside the cavities, in the way the bubble grows inside a cavity, and therefore a nucleation site, active nucleation site, the activity is affected by this contact angle hysteresis. So this brings us to the end of the lecture. We will just summarize by saying that boiling heat transfer involves heterogeneous nucleation and not homogeneous nucleation. That is what our focus is. And it is essentially a process of changing over from a liquid to a vapor phenomena. It is a very important heat transfer process in many critical engineering applications. Heterogeneous nucleation involves an interplay of Young-Laplace equation and Clausius-Clapeyron equation. Both should be satisfied during bubble growth. And wetting dynamics and physical morphology of the heater surface plays an important role in nucleation. So you will see later on that actually rough surfaces are good because many nucleation sites get active. And if you have a very smooth surface, then the boiling superheat or the wall temperature which is required for boiling to take place is rather high, and therefore not good for heat transfer applications. So with this, we close this lecture. If you have any questions, please feel free to contact me. Thank you very much.